let's talk about the composition of blood. So, I'm going to draw a little vial here. Okay. Just took out your blood. Boom. Full here. Bottom here. Okay, so right here we have a plasma, buffy layer, and erythrocytes. The plasma is like the liquid part of the blood, doesn't contain any cells. Erythrocytes, those are your red blood cells. Buffy layer is composed primarily of white blood cells and other cells involved with the immune system. Okay, now within the plasma, there's plenty of these proteins. The plasma is a colloid, which means there are proteins in suspension there. They haven't settled to the bottom yet. It's like milk. Milk has proteins in it that don't really settle to the bottom. Okay, so here we go. So we got these proteins. And then we got these proteins. And then, for good measure, we got these proteins too. Okay, 3 types of proteins within plasma primarily are albumin, albumin, drew with green, globulins, and fibrinogen. Albumin is just a large protein. It's there to basically support osmotic homeostasis, equilibrium. It's also used as a transporter of various lipid-soluble molecules. Globulins are antibodies. They're there for a reason, bind to viruses, bacteria that might be in your body, initiate immune response. Fibrinogen helps with hemostasis, which is what we're going to talk about later. You notice at the bottom here we have erythrocytes. Now, if we take this whole distance, the whole volume here, and then we take this part right here, the percentage of this whole thing that's just erythrocytes, that's called your hematocrit. And hematocrit's basically just a measure of what percentage of your blood is composed of red blood cells. And it will increase as you go up in elevation, you have less oxygen exposed to you, or you participate in cardiac exercise and you need more red blood cells. If you have anemia, iron deficiency, the hematocrit will decrease. And that is the composition of blood. Oh, I probably should erase this before. But I already have it drawn up here. So, okay. So, what happens in this pathway, red blood cells last about like 120 days, which is why we do a hemoglobin A1C every 3 months. Yeah, so what will happen is macrophages in your spleen, liver, and bone marrow, I imagine they know how to detect the red blood cells ready to die, will go in and they'll consume these red blood cells and they'll break them down. And they'll break them down into the heme. Did you know, I'll whip this fact out, that our body breaks down 2.6 times 10 to the 6 RBCs per second. That means every second we break down this many red blood cells because each one contains 250 million heme groups to carry oxygen. That means, we multiply that by how many heme groups we have per red blood cell, which is like 2.5 times 10 to the 8. That means we'll have 500 trillion heme groups that we have to break down every second. That's bonkers. Okay, so this is how it happens. This heme, there's enzymes in these macrophages. These heme here will get broken down by an enzyme called heme oxygenase, and it'll be converted to biliverdin. This change makes heme soluble in water. Heme is not soluble in water. Biliverdin will then get converted, furthermore, into bilirubin reductase. Bilirubin is not soluble in water. So why did we make that change? A lot of scientists think, and what the literature says, that bilirubin is a very potent antioxidant. And a lot of animals will just convert it to biliverdin and excrete it. That's why birds poop green. Biliverdin is green. So, but we think it's because this is such a potent antioxidant that it helps stave off damage from free radicals like superoxides that come from our aerobic metabolism. And so it actually extends our lifespan by, say, 30 years. So it's worth it because we have albumin. Albumin is a carrier protein in the blood. We talked about it in the composition of blood here. Albumin will go to the liver. That's my drawing of the liver. It's not very good. The liver will then process the bilirubin and put some glucuronic acids on that boy, and it'll send it down into the digestive tract. And bacteria see the glucuronic acids, which is like sugar, and they're like, oh, nice, I want to eat that. And so they eat it. Conjugated bilirubin will get converted to urobilin. This urobilin is soluble in water. It'll enter the bloodstream and eventually end up in our kidneys, which process it and excrete it out as urine, which gives our urine its yellow color. If the urobilin stays in the digestive tract, bacteria will then further convert it into stercobilin, which then has a brown color, which is then excreted as feces. So that, from start to finish, is how basically our body can process 500 trillion heme molecules per second. And that's why this process is so taxing. That's why, that's one way we get rid of toxins. That's why, because if they build up, it's just dangerous. So, yeah. All right, here we go. I think we're recording. Just want to make sure. Yeah, because I've made that mistake a few times. 1.6. All right, bet. All right. So, here we go. Hemostasis. How we avoid bleeding to death. There are 3 ways. Vasoconstriction. We have clotting. It's like clotting. Yeah, I'm just going to call it clotting. And then we have coagulation cascade. Formation of the fibrin mesh. All right, let's go over it. Okay, within our body here, I'm going to draw a little blood supply here. They're epithelial cells, and they're held together by what's called a basement membrane, or a collagen up here. We got collagen. Okay, collagen's slightly negatively charged, and there is a factor that floats around in the blood that's relatively inert until you have damage to these cells that may cause bleeding. We have the little protein here called von Willebrand factor. And we know about platelets here. Here's a megakaryocyte, and it will make these little platelets, basically fragments of this cell. And on these platelets, they have receptors that will bind von Willebrand factor, like that. Now, say I get a cut, scrape on my knee, need to clot up some blood. Boom! This von Willebrand factor will bind with the platelet to the collagen, and it will activate this platelet. So it looks like a weird little like octopus thingy. Boom. And within these activated platelets, there's alpha granules and dense granules. Alpha granules will release PDGF, clotting factor, von Willebrand factor, and I forgot the other one. Calcium. Oh, and fibrinogen. Yeah, that's right. Okay. These dense granules release ADP. Now these platelets have ADP receptors. ADP will bind, activating these platelets. It's just crazy positive feedback. More platelets will join. Fibrinogen will be released by the alpha granules. These platelets have, guess what? Fibrinogen receptors, which binds activated platelets together. Fibrinogen will bind activated platelets together, like this. PDGF, another factor, activating platelets. And as you can see, we have all these things happening and we start forming a blood clot. Okay. Now, this is why we get runaway positive feedback, and this is why our endothelial cells are constantly blocking. They're releasing factors that block this process from happening so it doesn't happen across the whole bloodstream. That would be horrible. We would die. So, that's how blood clotting works. But now, we have another form of positive feedback to prevent us from dying. And if we zoom in here, which I'm going to do, we're going to zoom in here, and I'm going to draw out the coagulation cascade. Let's erase this real quick so that we have enough room. Needs this top layer now. So, as we've already said, the collagen is slightly negative. Factor 12 is attracted to this, loves that negative charge. And so here's what it'll do. Factor 12, draw it in green. Actually, we'll draw it in blue, because this is the intrinsic pathway. We'll go, it'll bind, and it'll activate it. So we have active factor 12, factor 12A. Factor 12 is an enzyme, and it will bind factor 11 and activate it. Factor 11, guess what? Is also an enzyme, and it will take factor 9 and activate it. Factor 9 is also an enzyme, and it works with factor 8. That's right, yeah, factor 8. And it will convert factor 10 here into factor 10A. So I wrote this one in blue because this is the intrinsic pathway here. Intrinsic. Okay, now we got mast cells up here, those real tissue cells, and attached to them is factor 3, which is also called tissue factor. Also, I'll write out the name. This is Hagman. Hagman factor. Okay. Now this tissue factor, we'll do this in red, we'll take factor 7 and activate it, creating active factor 7. Factor 7 will then take our beloved factor 10 and activate it, making active factor 10. Now we're going to draw out the common pathway because this happens regardless. Intrinsic, extrinsic. This is extrinsic pathway in red. Okay. Now we have the common. Factor 10A needs an enzyme, or a cofactor to function. It's an enzyme. It needs factor 5. Factor 2, or prothrombin, can be converted to thrombin. Put prothrombin. We got thrombin. This thrombin will then take fibrinogen, factor 1, and activate it, turning it into fibrin. There's one more factor involved, and that's factor 13. This is fibrin, and this will form the fibrin mesh. It's a very long protein, and then the factor 13 will form crosslinks between the fibrin, forming a nice little mesh-like net to basically hold the platelet plug in place, give it some structure, so it doesn't just fall apart. And so that is how the coagulation cascade works. Yeah. Okay. Now we formed our clot, we need to degrade it. And so, because if a blood clot comes off, it can block blood flow to certain cells and kill them. So, what our liver does is it releases TPA, tissue plasminogen activator. This TPA will activate plasminogen. It's a cofactor converting plasminogen to plasmin. Urokinase does the reaction. Then what plasmin will do is it will degrade fibrin mesh that makes up a blood clot. Basically dissolving it, letting it dissolve in water, and thus we destroy our blood clot, and so that we can circulate blood freely and safely.